Alrighty, howdy everyone. We'll get started. Welcome to another review session. In terms of announcements, you have a quiz next week, either on Monday or Tuesday. That's going to be online like normal. And then you have an exam either Thursday or Friday. So like last time, I will be also having a review session probably Tuesday night on Zoom, and then that will be recorded and posted, and then we'll have an extended version of this review session next week to do any last minute questions. I'm putting together practice problems from last week. I just didn't get to it last week, and then I'll have additional practice problems for the exam for this week. So be on the lookout for both of those in terms of practice, and then I'll send out the announcement with the Zoom link next week when I confirm the time that I want to do it with. Any questions for me there? Alrighty. For today, I had a request to do intermolecular forces. Is that okay if we start there? Yeah, great. Okay. So when we talk about intermolecular forces, these are going to be known as IMFs. What does this tell us with our intermolecular forces? What are we looking at? Yep, so we're looking at the attraction between two molecules. Okay. This can be molecules of the same molecule, right? This could be an oxygen atom interacting with an oxygen atom, or this could be different molecules. This could be an oxygen atom interacting with a sodium ion, right? It depends on the solution that you have. It depends on the compounds that you're looking at. What kind of, or what are the types of intermolecular forces? I think there's 7. You can just shout them out. Dipole is one of them. What else? What else? That will be a group of them. So we'll show you what is the group of them. Anything else? So there's a category that is an ion-induced dipole or a dipole-induced dipole. I didn't spell that correctly. Okay. Those ones you don't need to worry too much about, but they are present in some solutions. Alrighty, so we have 7 intermolecular forces. Which one's going to be our strongest intermolecular force? Ion is our intermolecular force that is the strongest. What does it mean to be an ionic bond? What do you have when you have an ionic bond? You have a metal and a non-metal, right? And when we look at a metal and a non-metal, do they usually have charges associated with them? Yes, they do, right? It's an ion. An ion means it has a charge. So an example, right, is Na plus and Cl minus. Are electrons shared or transferred in an ionic bond? They're transferred, right? That means that their bond is so strong that the chlorine actually takes the electron from sodium, making sodium a positive charge and chlorine a negative charge. When we look at something like carbon fluorine, is this being shared? Are the electrons being shared or transferred? They're being shared. So what do we put as charges for our carbon and our fluorine? You need partial charges, right? So we have, what kind of partial charge does carbon get? Gets a positive, and fluorine gets a partial negative. And why does fluorine get the partial negative? Electronegativity, right? It's more electronegative. Yep. Right, so carbon gets the partial positive and fluorine gets the partial negative because fluorine's more electronegative, which means it wants the electron more than carbon does. What does this create with the partial positive and the partial negative? This is the dipole. Right, notice how we say partial charges. It has a partial positive and a partial negative. When we look at sodium chloride, that's a positive charge and a negative charge. Right? They're only sharing in the carbon fluorine, but they're transferred in the ionic bond. So it's so strong that the sharing is actually transferred. Okay, so that's why ion is going to be your strongest bond. Nope. So this is just so that's an example of a covalent bond, right? Because we have two nonmetals. Okay, any other questions there? Everyone see the difference between the covalent and the ionic and why ionic is stronger? Yes, okay. We're not going to worry about ranking these. Just know that they exist. I can explain them in a second. So next we have ion. What's going to be our next strongest intermolecular force? Yep, ion dipole is going to be our next one. Right, when we look at an ion dipole, this means that we have something like a sodium ion charge or a sodium ion cation interacting with something like a CF molecule, right? So you have this ion and you have this molecule interacting with each other. So you have a positive and you have a partial positive and a partial negative. Which way would the carbon-fluorine bond interact with the positive charge? Would it react carbon facing it or fluorine facing it? If fluorine would be facing it, why is fluorine going to be facing it? It's negative to positive, right? Just like a magnet. So this is actually going to look like the sodium ion, then the fluorine, then the carbon, right? Everything in the system is going to react this way. We're going to arrange this way. What does the sodium ion do to the dipole of the fluorine carbon? Does it make it stronger or weaker? It makes it stronger, right? We have now a positive charge. If we took away the sodium plus ion in solution, it would still have that positive negative charge from the dipole. But since we put the sodium ion with the carbon-fluorine bond, that positive charge from the carbon is going to draw the electrons closer to that positive charge, meaning they're spending more time hanging out by that fluorine molecule and less time by that carbon molecule. So it increases the dipole. So now it's more like, now it's more like this kind of dipole, right? Where we have a stronger dipole. Questions on ion dipole? Okay. What is our next strongest? Then we have hydrogen bonding. What kind of bond is a hydrogen bond in terms of ionic or covalent? This is a covalent bond. And what are our requirements for a hydrogen bond? Anything else? HN. Right, so hydrogen has to be directly bonded, right? Directly is the key word here. Bonded to an oxygen, fluorine, or a nitrogen. Okay, if you have something that's like this molecule here, can that molecule hydrogen bond? No, right? Because the hydrogens are only bound to the carbons. There's nothing bound to that oxygen. So this one is no hydrogen bonding. But what's an example of a hydrogen, or that's something that can't hydrogen bond? Or does have hydrogen bonds? Water, yep. Right, water can hydrogen bond because the hydrogen's directly bound to the oxygen. This is a special case of dipole-dipole interactions, but they are stronger than your dipole-dipole interactions. Okay, so like ammonia and HF, right? Those are both examples of hydrogen bonds as well. Any questions on hydrogen bonding? Alrighty. What's our next strongest intermolecular force? Dipole-dipole. What's our requirements for a dipole-dipole interaction? Yep, we need polar molecules. What does it mean for something to be polar? We have a positive and negative. Uneven distribution of electrons. What causes the uneven distribution of electrons? Lone pair might do that. What else? Asymmetrical. What did we say caused the dipole between carbon and fluorine? Electronegativity, right? So in order to be polar, we need a difference in electronegativity. What's our trend for electronegativity on the periodic table? If we're going across the periodic table, left to right. Yep, electronegativity is going to increase. What if we're going down the periodic table? Decreases. So where is our most electronegative atom? Fluorine. Yep, so we look at periodic table here. Right, as we go left and up, we're going to get more electronegative. So fluorine is our most electronegative atom. What's an example of a polar molecule? Water is a polar molecule that we know that can also hydrogen bond. Anyone know anything else that's polar? The compound I just drew up here is polar. Bless you. Yep, HCl is polar. Right, so all of these can have dipole-dipole interactions. So when we look at the hydrogen and oxygen in water, which one is more electronegative? Oxygen is more electronegative, so which way is our partial negative and which way does our dipole point? It points towards the oxygen, right? So this is going to be your partial negative. So our dipole points towards the negative. And that's going to happen on both sides, right? So those bonds are polar, they're pointing towards each other. But why don't those cancel out? Right? It's overall, we're looking at a positive upward arrow, the way that I drew it, because the shape is tetrahedral, right? It's a three-dimensional shape. The lone pairs are going to take up more space than the bonds do, and so that gets all disoriented, right? So we do have an overall positive, net positive for our dipole interaction. Okay, when we look at the middle compound, what's the difference in electronegativity between hydrogen and carbon? It's a trick question. We're going to count that as not polar. So between hydrogen and carbon, there is no difference in electronegativity. What about between carbon and oxygen? Is there a difference in electronegativity? There, yep, oxygen's more electronegative. So this one, we have our positive charges pulling this way. And for the same reason that the hydrogen, or I'm sorry, the water is polar, this other molecule is polar as well, right? You can just think that instead of putting hydrogens on the left and right hand side, we just put a CH3 instead. So it has the same shape as water in this case. So that makes it still polar. They're just, it's so small, there's really no difference in electronegativity. Yep. That's the only one. Yep.
Larger compounds like that, will you always only look at like the center molecule or like the center atom?
You want to look where there's like a lone pair usually. Because you could get like some larger molecules where it's like this here, and these all have hydrogens bounded off next to it, right? So technically the carbon is the center, but the oxygen is the thing that's going to make it polar. And that's because that will have lone pairs on it. So if you see a lone pair, start there. Yep. Is that enough? I'll post this afterwards too. Yep. Yes, did I draw a partial positive? That's sorry. Yep. Yep, so it's the partial negative in front of the oxygen. Does that help answer questions? And then lastly, looking at between hydrogen and chlorine. Chlorine's going to be more electronegative, so that gets the partial positive, or that gets the partial negative, and the hydrogen gets the partial positive. Okay, when we talk about covalent bonds and the hydrogen bond, the dipole-dipole interactions, these can be applied to both pure substances and also mixtures. So if you have something that's just water, right, pure water, that will have dipole-dipole interactions and hydrogen bonding because water has both of those. If you look at something like water and HCl mixed together, that now only has dipole-dipole interactions because they cannot hydrogen bond between each other, right? The oxygen atom is not gonna hydrogen bond with the HCl. You need something that both has hydrogen bonds there. So that way it's just dipole-dipole interactions. Does that make sense between the two? So you tell me. So if we have water, this has the partial negative, this has the partial positive. Where is the hydrogen chloride gonna line up with, right? So, right, what did we do? What did we do between the sodium and then the carbon and fluorine? What did we line up? The opposite charge. So that's going to happen again here, right? So if we're looking at the oxygen, what's going to be closer to that, the hydrogen or the chlorine? The hydrogen, right? So something like HCl might end up here, right? Because this would be the partial positive and the partial negative. And then the hydrogen, right? So that's going to be just for the oxygen. But then the chlorine over here is going to start interacting with the positive charge of the hydrogen. Okay, and then that keeps building up, right? This might have an oxygen here that it bonds to, and that's what holds them all together. It's because those charges can interact in their partial and their opposite. That's what keeps them so tight.
You're saying that there's only a dipole.
Yes.
But if you were just to look at the H2O, then you would have the hydrogen.
Mm-hmm. Yep, because they can hydrogen bond with itself. Does this make sense how this gets lined up when you have two compounds together? Yes.
H2O did bond with itself. How would that?
So if we're looking at just water, what's going to interact with the oxygen? Another oxygen molecule or the hydrogen molecule? The hydrogen, right? So the hydrogen is going to stay close and have this here. And if we looked at the hydrogen, what is going to interact with that? The oxygen, right? So the oxygen is going to come down here. Right? You see how that works? Right, don't worry about the little partial in front of it. Just keep on lining up the positives and negatives. Alrighty, any other questions on dipole-dipole interaction? Alrighty. And what is our last intermolecular force, our weakest? This is London dispersion forces, or just LDFs. What molecules have LDFs? All molecules will have London dispersion forces. Even nonpolar molecules? Yes, even nonpolar molecules. Polar molecules, nonpolar, right? All of these will have them. So if you have dipole-dipole interactions, you also have London dispersion forces. If you have hydrogen bonds, and you also have you also have dipole-dipole, which means you also have London dispersion. Does anyone know what causes the London dispersion forces? Electrons are constantly moving. So, right, if you just have two electrons, sometimes they're going to end up both closer to one atom over the other. If electrons are going to be positive charge or negative charge? Negative, right? So at some point, maybe in hydrogen bond here, then maybe both electrons end up on this side. They're negative, so they're going to create a quick partial negative charge, creating a quick partial positive charge. That's going to interact with, right, another molecule right next to it. And so since this makes a partial negative, that's going to push the electrons away, creating a partial positive and a partial negative here. And that keeps on building up. But the electrons are constantly moving, so this dipole is constantly changing, and that's what's holding all of the atoms close together, is because of these electrons constantly moving around the atom. All right, so it makes the nonpolar molecule polar for just a split second, and then it's gone. Or then it's in a different direction. Okay, any questions on intermolecular forces. Does this help clear up some things? Okay. Let's do. So I want to. Okay, so you have three questions here. So looking at what are the intermolecular forces holding together the CH4 molecules with each other? What about the NH3 and the H2O between each other, the mixture of those? And the CH2, sorry, this is Cl2, and methanol, which is CH3OH. Give you a couple minutes, work on this. And I want to list all of the intermolecular forces. So if there's more than one, write all of them down.
Economics.
Mhm. Bless you. Alrighty, what do we have for A? What's going to be the intermolecular forces for CH4 and CH4? Yep, this is just London dispersion forces. Right, is CH4 a polar or non-polar molecule? That's non-polar. So if we were right, we're just looking at CH4 molecules, and then, right, we have the same thing. This is a pure substance, right? So if it's two nonpolar, then the only thing holding them together is London dispersion forces. Okay, what about NH3 and H2O? Yep, we have LDF. We have hydrogen. Anything else? Yep, and then we'll also have dipole-dipole. So hydrogen bond is a classification of dipole-dipole. So if you have a hydrogen bond, then you also have to have dipole-dipole. Yes, it's like if, right, all hydrogen bonds are dipole-dipole, but not all dipole-dipole are hydrogen bonds.
It is, I know that you just said that, but like, it's dipole-dipole also because like H2O is polar and H3 is.
Yes. Yep. Yep. Right, if hydrogen bonds didn't exist, like it would still be a polar molecule. So that still makes it dipole-dipole. Alrighty, and what about our last one? CH2Cl2 and CH3OH. We have LDF. Anything else? So just between CH3OH and CH2Cl2, we don't have any hydrogen bonds, right? We just have dipole-dipole. It's because of the definition of the hydrogen bond. Right, so you need to have this HOH situation or HNH. And then, right, this also has to be paired to another oxygen or another hydrogen. But since right, since it's looking like this second hydrogen to carbon doesn't count as the hydrogen bond. So I guess if you see that there is no, right, there's no compounds, there's no, right, there's none of the HNHOHF in the H2Cl2. So you know that that one can't hydrogen bond. Yes. Yep. Right, if we just had CH3OH and CH3OH, then this would have hydrogen bond because they can hydrogen bond with each other. Right, it's the same molecule. Yep. Yes. Yep. And they'll only give it to you if it's a hydrogen bond if both of them have each component. Okay, does everyone see the difference between those two? Is that CH2Cl2, is that a polar or non-polar molecule?
Polar.
It is polar, right? That's tetrahedral, so the shapes are going to be all wonky. It's not two-dimensional. So those difference in electronegativities will cause an overall polar molecule. Yep.
You have two molecules that like both have like either HNO or HN.
Mhm.
So I'm actually assuming that there will be.
Yes. Yep. Yeah, if both of them satisfy the HNHOHF, then they would be hydrogen bonds. Anything else? Does that make sense that you can identify them between two compounds? Okay, and then you can do the same thing, right, as in A. if they're looking for something that says, you know, what would hold these molecules together and it's a pure substance of water, right? Just look at what would interact with that and what kind of hydrogen bonds or polar molecules it may have. Alrighty. We'll move on to polarity. What about polarity are you looking at? Like polar molecules?
Kind of just like identifying if they're not polar polar based on the symmetry.
Yeah, yep. Um, okay, so if we have something like, yep. Okay, let's look at these three compounds first. So if we're looking at NCl3, I'm gonna have you take a couple minutes, draw the Lewis structure for all three of these. We'll have you practice that first. Mhm. Mhm. Yep, so if you look at fluorine, where is chlorine in relation? Right below. Where is nitrogen? And so we'll call that one, right? It's one away. How far is nitrogen away? 2. So since chlorine is directly attached to fluorine, that one's going to be more electronegative than the nitrogen. Yep. Pretty much everything. Yeah. And they probably would also give you the electronegativity values on it. So you can do the subtraction between nitrogen and, or you can see what value is larger. And then that one would be your most electronegative. So I think chlorine's like 3.7 and nitrogen's like 3.3, right? So you can, 3.7 is larger.
Obviously the best structure for this.
Yes, yes.
Quick equation for that again, it's valence electrons minus dots plus lines.
Yep, it's valence electrons minus dots plus lines. Minus dots plus lines in parentheses. Do that first. PEMDAS. Right, and what's that formula for? What is that called? Mhm.
What the lowest number?
Yes, yep. Or you want the least amount of formal charge. You want them to be 0 if possible. Alrighty. So here are your three structures that you should have come up with. As like a kind of hint, if you see a nitrogen and three compounds, right? So like NH3 is a good example. Nitrogen's usually going to end up with 3 bonds and 1 lone pair, right? It likes it that way. CH2O will always look like that structure. It's a ketone. And then sulfur, SO2, that one you just kind of will have to do over and again. I usually have to draw all of that one or like do all the steps to get that one. That one's just not as common. Okay, any questions on how any of these things look? Yep. Oh, because I just didn't put them on. So your least electronegative atom is going to go in the center, or the thing you have one of. So in the case of NCl3, you only have 1 nitrogen, that one should go in the center. And then in the case of sulfur dioxide, right, you only have 1 sulfur, that one should go in the center. Yep. Is there a charge on? You could. You could do that as well. That's fine too. So you could also do. You could do that. I think this just makes the formal charges a little wonky. Maybe. No, it doesn't. That gives it 6. Yeah, that's fine. Yeah, that's fine.
For that SO2, like, deciding which ones, that is one of the best. But like, with the, like, how you're saying there's one way or two way,
Mhm.
since S and F are like diagonal. How,
So because, right, electronegative, so oxygen is 1 away from fluorine, and then you go down the period, or you go down the periodic table, electronegativity decreases. Yep. Yep.
Which one is the preferred one for SO2?
Probably probably the top one because it doesn't have to expand its octet. That one has formal charge, but I think it prefers to not expand its octet over expanding its octet.
Charge, is that, I forgot, is, do you do that for each of the atoms in the molecule or for the total?
For each of the atoms in the molecule. So for NCl3, you could technically solve for 4 formal charges. 1 for the nitrogen and then the 3 chlorines. They'll all be the same. But yeah, you can solve it for each atom. Yep. So if you look at this one here, this one would have a resonance structure. So technically, right, it's gonna flip-flop between the top one in the box, that middle one, and then the one where the double bond is on the other side. So when you say preferred, it's gonna be a hybrid of like all 3. So you just need to know that there's resonance involved. Right, SO2 would be something that you would ask like, is there resonance? And you would say yes. Not necessarily ask questions about the shape. Any other questions? Okay. When we look at NCl3, what is the electron domain geometry? Tetrahedral. And why is that? Good, we have 4 electron domains. We have 3 from the bonds and 1 from the lone pair. Everyone sees the 4 electron domains. What is the molecular domain geometry? Trigonal pyramidal. Right? So I like to think of a tetrahedral as a tripod. It kind of works, right? If you think about the feet coming down and then like where your phone would sit to, right? That's kind of what the trigonal, or that's what the tetrahedral is going to look like. So if you take one of those bonds away, right? If you take your phone away and you just have the tripod, that looks like a trigonal pyramid and hence trigonal pyramidal, right? So that's where the molecular domain comes from. And if you're a visual person, maybe that helps. Okay, do we have polar bonds in our nitrogen chloride bonds?
Yeah.
Yep, which one's more electronegative? Chlorine is going to be more electronegative, so which way are our bonds going to point out? Yep, so we're going to point towards the nitrogen to chlorine. Do we have symmetry in our? No, right? So even though if we're looking at the tripod, right, they kind of look similar because they're all three, right? You have this lone pair floating out above. This is going to push your electrons closer together or your electron domains that are in the bonds closer together, and that messes up the symmetry. And so you'll actually be pulling that electron domain down. So overall, we do have a polar molecule. Then it would be nonpolar. Yep. But that would be only if we had 3 electron domains. Usually with a lone pair, you're going to be a polar molecule. There's only, I think, 2 instances where there's lone pairs and you still have a nonpolar molecule. If you have, we'll get to that in a second. Yep. Nope, so that would still, so if it's CH3, then carbon would have a lone pair, and that would make it polar. Yep. Because the lone pair is now going to screw up the symmetry between all of that. Okay. Everyone sees that this was an overall polar molecule. What about CH2O? What is the electron domain geometry here? Trigonal planar. Okay, notice the difference between trigonal planar and trigonal pyramidal. Planar has plane in it, right? That means that you can put a piece of paper on it. You could, right? It's on your piece of paper. It sits flat on your plane. The trigonal pyramidal would come out of your plane, right? It would be sitting like this on top of your screen. Ooh, sorry. Right, it'd be sitting like this on top of your screen. The planar lays flat. We're almost done now. What is our molecular domain geometry? This is also trigonal planar. Right, we have 3 electron domains. We have no lone pairs, and so your electron domain and your molecular domain geometries are going to be the same. Do we have any polar bonds in this compound? Yes, what is it between? Yep, oxygen and carbon. Which way do they point? They point from carbon to oxygen. So they point up towards the oxygen. So is there symmetry? Do we have a polar molecule here? We have a polar molecule. Yep. Yes. Yep. Technically, because the oxygen and carbon creates a partial positive for the carbon, you'll actually get little dipoles pointing here. And so that just contributes to the overall upward dipole that we have pointed for our molecule. No. So if you were like asked to draw the structure and asked to draw the dipoles, you would just draw it for the carbon oxygen. All right, but there's nothing canceling out a negative arrow, or there's nothing pointing down, and so there's only that net positive or that net pointing upwards dipole for this molecule. Any questions on CH2O? Alrighty, and then the last thing we have is SO2. So no matter what structure you look at, what is our electron domain geometry? This one is trigonal planar. Right, it starts off with 3 electron domains. Right, we have 1, 2, 3. What is our molecular domain geometry? This is bent. Right, we have 1, 2, 3. We're gonna create a lone pair that's gonna bend our bonds for SO2. So it's actually gonna look like this. Right, gets a little bent. Think of like the water molecule, that kind of bent. Do we have polar bonds between our atoms here? Yes, we do. Where do they point? They're going to point towards oxygen. So do we have a polar molecule? Yes, we do. Yep.
Nitrogen was more portions.
Nitrogen will be more electropositive. That one's about 3.3, and then carbon's about 3.7 in terms of electronegativity.
So like if it's or like not, it would be not.
Yes, if it was straight across, if there was no lone pair on the sulfur, then it would just be a linear molecule. They would be pulling in opposite directions, right? Think tug of war. And so there's nothing to, right, that's going to cancel each other out. But if we're looking at like sulfur and oxygen and we're thinking about the dipoles, how we drew it, we're both pulling this way. Which way do my hands go? They go out and down, right? They're going down. So they're going to cancel each other going towards the sides. But if we look at the vectors, then it's still going to go down.
So we're looking at the molecular domain thing to figure out.
Yes. Yep. Yep. If electron domain geometry is just to help you figure out the molecular domain geometry. Yep. The electron domain geometry helps you figure out the molecular domain. Yes. Yep. Something needs to be asymmetrical. Yep. Yes. So there are 2 instances of that. Does anyone know the 2 instances? So there can be, I'm just going to give this M's and X's. So you have this shape here. What is the electron domain geometry for this one? This is trigonal bipyramidal. What is the molecular domain? This is now linear. Where are those lone pairs in your? Yep, yep. So all lone pairs here are at the equatorial position. So that's like taking your equator, right? And you have a triangle coming out of your equator. It's flat, and then you have one pointing this way, and then your triangle is pointing that way. So since all of those are sitting in the same plane, all of them are pulling and distributing in the same direction. So your X's here would be sitting axial, right? So think about going from North Pole to South Pole. So whatever is opposite those are going to be canceling each other out, whether they're polar or non-polar. So here's a case where there's lone pairs around the central atom, but still a nonpolar molecule. Assuming these are the same, right? You could also have, right, something like this. Now you have opposite atoms, both in the axial position. So depending on their electronegativities, they might not cancel. Yes, yep, whether they're pointing out or in, they would still cancel each other out. Yes. Yep. Right, because you just think about the north and south pole, right? If they're both pointing in or they're both pointing out, they're still in the same straight line. And so that would cancel each other out. This one is nonpolar. This one is polar. Mhm.
There wasn't that linear, even though it has two different types of bonds, it's still be nonpolar.
So if it had a single bond and a double bond, we said that there was also resonance. So does it actually look like a single and double bond? Right? So it's actually going to be the average of the two, so they would be the same. So it would be nonpolar. It would probably just be included in your question at the very. Nope. Nope. Still know your trends, because they might give you like which one is in order of increasing electronegativity based off of the trend. You should be able to do that with no values. But looking at like which one's more polar or something, they might give you values for that. In terms of what?
Is that electronegativity works for 3 and 6 that have exceptions? Or is
That's ionization energy. Yeah, that one you should know. The ionization energies you should know that trend in the exceptions. But that does not apply to electronegativity. Yep. Yep, so in group 3 and group 6, I'll tell you that in a second. Let me just finish the other example.
Oh, yeah.
So then the other example is if you have, again, this. Right, what is your electron domain geometry here? What is your molecular domain geometry? Square planar. Where are your lone pairs this time? These are in the axial position, and all of your atoms are in the equatorial position. So all of those are in a plane, right? Think of them as pointing towards the corners of a square. And so those are all going to cancel out. So this is lone pair and nonpolar. Yep. Well, right, they're pointing out. So if you pull in diagonal directions outwards, then they're going to cancel. But if you, right, have two cars driving at each other and they hit, that's going to cancel out as well. Right? So that's, right, just think about the arrows colliding and then stopping in the center. Questions? Yes.
Summarize, let me make the
Yes. As long as they are both in either the same axial or equatorial, right? For the first one, those were all in equatorial lone pairs. And the second one, they're in axial lone pairs. They just need to be in the same plane. Yep. Yes. Yep.
Is it possible for the octahedral to have 4 lone pairs?
No, usually the octahedral either has no lone pairs, 1 lone pair, or 2 lone pairs, and that's it. To make the molecule nonpolar. Any other questions on the shapes? Okay, and then the exception real quick is ionization energy. So in group 3, you have all of your electron configurations looking like this, where this is the s orbital and this is the p orbital. So the ionization energy actually goes down to remove the p orbital electron, because then it ends up with just an s electron that's filled, right? You have nothing unpaired. So, right, going from group 1 to group 2, ionization energy increases, so it's like 1, 2, and then group 3 is down here. And then it goes 4, 5, and then 6 is down here, because at 6, you now pair up a previously unpaired electron. So it would rather be unpaired than have one paired electron. So it's easy to remove that 6th electron. And it goes back up 7, 8. Any other questions there? Alrighty, with that, I'll call it good for this week. If you have any questions, just let me know. And I'll look out for an announcement for me for a Zoom next week on Tuesday. Probably like 8 o'clock again. I will let you know.
Okay. This was on the homework. And I ended up just